Hi everyone, let's get started while more people are joining. Welcome to this M2D2 talk. Today we are going to be talking about PoseBuster, an AI docking, and why AI docking method failed to generate physically valid poses or generalize to novel sequences. The talk today will be given by Martin Buttenschoen, who is a second year PhD student at the OP group at University of Oxford. And his research is mainly focused on applied machine learning for de novo drug development, especially small molecule post-prediction, also known as small molecule docking. Thank you so much, Martin, for being here today and sharing this work with us. Before we get into it, this will be a short one, so rather 30 minutes or so in terms of presentation. So if you have any question, please write in the chat, and right at the end of the presentation, Martin will be taking other questions. So thank you so much, Martin, and let's get into it.
Well, thank you very much. Thank you very much for giving me room to present my work that I've been doing for my DPhil under the supervision of Garrett Morris and Charlotte Dean, which is titled PoseBusters, AI-based docking methods fail to generate physically valid poses or generalize to novel sequences. Before you start, I hope that you like a certain 80s TV show as much as I do. So if a molecule is strange in your binding site, who are you gonna call? PoseBusters. If there's a ligand pose that doesn't look right, who are you gonna call? PoseBusters. To motivate my talk, I'm gonna show you four numbers, four RMSD values, which are root mean squared deviation values that measure how close a docking prediction is to the ground truth it is trying to recover. Those four numbers are 1.6 angstrom, 2.2 angstrom, 1.0 angstrom, and 1.3 angstrom. Typically, one takes 2.0 angstrom as a threshold to decide whether a docking prediction in terms of RMSD is good or bad. And these are all below or close to 2.0 angstrom. If I now also showed you the predictions, what these molecules would look like in 3D, and then the corresponding crystal structure, you'd see that the shape of these molecules, the poses generated, while they might be within 2.0 angstrom RMSD, they do not look physically valid. If you show those to your chemist, chances are they might stop speaking to you entirely, especially with the molecule in the middle that looks like a pretzel. Because pretzel is not a molecule shape, you will not see internal clash as shown in this molecule ever. So we can see that RMSD values can be good, but the poses might look bad. So PoseBusters actually helps you with this because it provides checks for molecular poses predicted by docking or de novo molecular generation methods as an additional metric to RMSD. PoseBusters is built entirely using RDKit, which is an open source Python toolkit to do things just like this. So thank you, Greg Lendrum, for actually making this open source and available. PoseBusters consists of three sets of tests. The first set is chemical validity and consistency. So here we check whether the molecule that we meant to dock is actually the molecule that we get out of it. So we check that the molecular formula, that the bonds connecting the atoms are the same, the chirality is preserved, and that it is still a valid molecule, so passes RDKit sanitization check. The second set of tests is intramolecular validity, and here we check the geometry of the ligand. So we check bond lengths, bond angles, and the distances between non-covalently bounded atom pairs in the ligand against bounds that we obtain from distance geometry. These are, by the way, used in ETKDG version 3 to generate molecular conformers. We also check whether systems which we expect to be flat are actually flat. So here, this is planar double bonds and planar aromatic rings. And lastly, we check internal energy of the ligand conformation. And here we use the approximate energy as calculated by the universal force field. The last set of checks is the intermolecular validity. And here we check how the ligand is positioned relative to the protein and cofactors in the docking scenario that we're looking at. These come in two flavors. The first one is we just check the minimum distance between protein and ligand or cofactors. And the second one, we check volume overlap. So PoseBusters is a command line tool and a Python library. You can install it from PyPy with pip, just so. And then you can use the bust command on a molecule file or a molecule file and the protein file, and it will give test results just like unit tests in Python would. So for all the molecular conformations in your file, it will print out the conformation name, and then it will print the set of tests that it has checked and whether they pass or fail. If they fail, it'll show up like this. You can also save the results and further information in a table using the CSV option. So we use PoseBusters to check machine learning-based docking methods. And the first thing that we do is we take a well-established test set, the Asterix diverse set, which contains 85 diverse target proteins and 85 unique drug-like ligands. It's an older data set. It was released before 2007. And it is, and what we do is we take this data set and we redock a flexible ligand into rigid protein receptors. And as a baseline, we use two classical docking methods, Vina and Gold, and compare against deep learning-based docking methods, DeepDock, Uni-Mol, and 3 deep learning-based blind docking methods, TankBind, DiffDock, and EquiBind. Those are just 5 deep learning methods, and they were chosen to be a representative set of different machine learning approaches that are currently being tried out on docking. DeepDock uses a Gaussian mixture-based statistical potential. Uni-Mol uses an SE3 equivariant transformer. TankBind uses a trigonometry-aware neural network. DiffDock is a diffusion-based equivariant graph neural network-based docking machine learning method. And EquiBind uses just the EGNN. So what is important to note here is that each method defines the search space slightly different. So I'm going to show you how we define search spaces to compare these methods. For Gold, we use the sphere of radius 25 angstrom, which is centered on the geometric center of the ground truth, the crystal ligand. For Vina, it is a cube. For DeepDock, we select the protein surface within 10 angstrom of any crystal ligand atom. And for Uni-Mol, we select protein residues within 8 angstrom of any crystal ligand heavy atom. The blind docking methods, DiffDock, EquiBind, TankBind, they're given the entire protein. And based on this comparison, all our results, so based on those definitions, we show our result. So what do we see? With this protocol, we get this picture. On this graph, we have the methods on the x-axis, grouped into classical, deep learning-based, and deep learning-based blind. And on the y-axis, we have the percentage of predictions that are within 2 angstrom RMSD. So the higher, the better. And roughly, DiffDock is the highest bar. So we say, well, it's beating the classical method. Well, we already learned we cannot trust RMSD alone. So what we do on top of calculating the RMSD is we require passing the PoseBuster checks. So after making all the predictions, we run the predictions through our test suite in order to determine whether they are physically plausible. And when we do this, we now look at the solid bars. So previously, we only had the shaded bars, which show how many predictions are within 2 angstrom RMSD. And we have now added the solid green bars, which in addition to 2 angstrom RMSD, require a physical validity. So again, how this happened is we had 85 test cases. And for the case of TankBind, we removed 35 predictions where the RMSD was above 2 angstrom, leaving us with 50 RMSD within 2 RMSD predictions, which is the striped bar, the 59%. And then in addition, we removed all of those predictions which failed one of the tests, leaving us with 5 out of 85, that is 5.9% on this chart. So the first main takeaway here is that previously, if we only look at RMSD, we would have concluded that DiffDock is better than the classical methods, and therefore deep learning-based methods outperform classical methods. However, if you also require physical validity, the tables turn and the classical methods outperform the deep learning-based method. So this is the first takeaway from our paper. Overall, I'm trying to tell you that PoseBusters is a good way to identify ways to improve docking methods. And the first takeaway is that good RMSD alone does not guarantee physically plausible predictions. We've seen this in the motivation slide, where I showed you the 4 numbers alongside the 4 structures. And now we've seen, if you use an old test set, that the actual ranking of the methods changes based on whether you use RMSD versus RMSD and physically plausible tests. Well, the second takeaway that I'm going to present is that deep learning-based methods are not yet better than classical methods. And what you have to remember is that these are machine learning methods which are trained on a certain data set. And the ASTIX diverse set actually consists of a lot of complexes which are actually used to train these methods. So it is not really a fair way to evaluate these methods. What we should actually do is we should take a new data set, something that these deep learning-based methods are not or have not been trained on. And the way we do this is we create a new data set from the PDB, the protein database, and we select 308 diverse proteins and 308 unique ligands, which were all released since 2021. Why 2021? Well, because the deep learning-based methods, all 5 of them, they were trained on some subsets of the PDB-bind general set, version 2020, which includes only complexes up to 2020. So by choosing complexes which are newer than 2020, we guarantee that these are new entries to the PDB. We repeat our analysis and add the bars that we get from this analysis to the previous chart that I've shown you. Again, to reiterate, on the x-axis we have all our methods, and on the y-axis we have the percentage of predictions which are in the striped bars within 2 angstrom RMSD, and in the solid bars, the predictions that are within 2 angstrom RMSD, as well as physically plausible according to our tests. And what we see now on the new data set, which is shown in red, the classical methods, they perform better than the deep learning-based methods in terms of the striped bars, which is just the RMSD, but also in terms of the solid bars, which is RMSD and physical plausibility. So this is our second takeaway, that with and without plausibility checks, only given new data, classical docking methods still outperform deep learning-based methods. And I'm going to show you 2 failure modes, for example, that show how these deep learning-based methods fail right now. And one of them is bond lengths. So bond lengths, just to recall, we check against the thresholds from distance geometry. And if a bond is longer than 1.25 times the upper threshold from distance geometry, we label this bond as being too long, and therefore this test has failed. For the 2 methods, Uni-Mol and TankBind, which actually predict variable bond lengths, we see that there's a certain number of predictions which is just way too long. We see that the longest bond for Uni-Mol is about 3 times the upper bound of the distance geometry, which is physically implausible because a carbon-carbon bond is never going to be 4 or 5 angstrom long, at least not for what we're trying to do. The second failure mode is steric clash, and here we look at pairs of atoms from the protein and the ligand, and we measured the distance between the two relative to the sum of their van der Waals radii. And if this distance is shorter than 0.75 times the sum of the van der Waals radii, we determine the pair of atoms to be in clash. And here we see that all of the deep learning-based methods predict clashes. And therefore, we labeled those predictions as non-physically valid. Interestingly, the classical methods also predict a low number of clashes. This is not perfect. As a side note, those thresholds we set so that all the crystal structures would pass all the tests. So that's why you can see that the crystal structures, which are shown here on top, pass both the bond length check and the class check. So this is the second takeaway from our paper, and that was that deep learning-based docking methods are not yet better than classical methods, given our new data set. And now I'm going to show you the third takeaway, and that is overfitting is a problem for deep learning-based docking methods. So in the data set that we generated, we have proteins which are new, and we have proteins which actually have been observed in a PDB before. So we split the PoseBusters benchmark set into 3 bins based on sequence similarity, sequence identity to the PDB-bind general set. And the bin that is going to be the most interesting is the low maximum sequence identity. So in this bin, we put in all those new test cases where the protein sequences are maximally up to 30% sequence identity to the PDB-bind general set version 2020. So this then is the set of proteins which are most probably structurally and functionally very, very different to those that these methods have been trained on. So it's going to be the yellow set. If I showed you now the same plot as before, but now we tease apart the sequence identity bins, we can see that the classical methods, Gold and Vina, perform about equally well on all of the bins. So that means for novel proteins, they perform about the same as the proteins which are in the PDB-bind general set. This is not the same for the deep learning-based methods. For DiffDock, for example, the bin with the new proteins, the 0 to 30% maximum sequence identity bin, performs much, much, much worse than the bin of the proteins that this method has been trained on. So based on this observation, we say that deep learning-based methods overfit on the proteins in the training set, and they perform worse as proteins with novel sequences than those proteins which are in the training set. So this was our third main takeaway, and that was that overfitting is a problem for deep learning-based docking methods. Now the last and fourth takeaway is going to be that some physics has not yet been learned by deep learning-based docking methods. And the way we're going to show this is we add a post-docking energy minimization step to our prediction pipeline. So after we have done the docking with the docking methods, the prediction of the poses, we add an energy minimization using a molecular dynamics force field. And here we take the amber force field and the sage small molecule force field, and we use OpenMM to minimize the energy of the ligand positions, keeping the protein completely fixed. And we optimize until convergence. So if we do this now and we compare against the results we had before, so now this is not based split on sequence anymore, but this is now the entire PoseBusters benchmark set again. Those are the same red bars that you've seen before, but now we've added in purple the predictions that you get after running energy minimization. we can see that the deep learning-based methods predictions have been improved. So what that means is some of these predictions which previously failed the test, be it for bond lengths or clash, they have been repaired by the energy minimization. And therefore, we say that there is some docking relevant physics that is not included in deep learning based docking methods that is included in the force field. And that gives us our last takeaway. And that was that force fields contain some docking relevant physics that is not included in the deep learning based methods because energy minimization repairs the method's predictions. So that was the fourth takeaway. So there you have it. Those are the four takeaways. First, good RMSD alone does not guarantee physically plausible predictions. Second, deep learning-based docking methods are not yet better than classical methods. Thirdly, overfitting is a problem for deep learning-based docking methods. And lastly, some physics is not yet learned by deep learning-based docking methods. I would like to acknowledge my supervisors Garrett and Charlotte and the rest of my research group, the Oxford Protein Informatics group, for providing an excellent research environment and fantastic mentoring. And if you'd like to know more, you can read our preprint, which is on arXiv. You can find the code on GitHub, and you can read the documentation online as well. And if you have further questions, you can reach out to me as well. Well, thank you very much.
Thank you so much, Martin. That's a fantastic talk. If you have any question, please raise your hand and open your mic or write in the chat, and Martin will be able to take that. Brad?
Hey, thanks. Thanks for this really practical work. Certainly you showed a lot of like detailed pose validity points, but going back to the RMSD, I'm curious about how you think about putting a high degree of importance on the RMSD from a crystal structure versus what poses are likely thermodynamically sampled in the cell. And I realize this question is a bit, slightly unrelated to the PoseBuster work, but you did use RMSD as a starting point. So I was just curious about how you view RMSD from the crystal structure versus the real thermodynamically relevant biological ensemble.
That's a very good question. So I would answer that we don't believe that the crystal structure shows the entire truth, but we believe that if you have a docking method, it should reproduce what we know, and that is the crystal structure. And a docking method that reproduces the ligand in the crystal structure, by the way, we actually have to have measured the protein with the ligand to actually have the protein in this case. That is sort of the easiest you can possibly make it for a docking method. This is not, biologically, like in the biological system, actually, what you might observe, given that you might actually get an ensemble over different poses. But given that's what we train these methods on, they should recover RMSD almost perfectly.
Yeah, got it. I didn't mean to be critical of your approach. You have to start somewhere, right? And so certainly using RMSD for the crystal is, it's well justified. I would say, I guess the direction I was thinking along the lines of is that, well, certainly if you have wrong bond lengths, that's going to be a bad pose. But if, let's say, bond lengths are good and you have, let's say, a globally high RMSD, it may be hard to rule out that particular pose is not sampled in vivo if perhaps, the deep learning method is implicitly capturing something from looking at multiple other crystal structures in training. But I'll drop off after here to give everyone else a chance to chat as well.
I think that's very interesting. I guess the only thing I can say on top of that is that the tests they are very conservative. So if you fail one of those tests, it means you have done something horribly wrong. Just because you pass all of the tests in the test suite as they are defined doesn't mean you have a good pose. So it could be that you pass all the tests and you actually don't, you have something like you have a false positive in a sense. And if you fail these tests, I cannot stress this enough, is like you have a bond length that is so out of whack that your chemist will stop talking to you. And that goes for all of those tests.
Got it.
Yeah.
Thank you very much. I appreciate it. Great talk and project.
Thank you, Brad.
Thank you.
Sebastian?
Yeah, so could you comment on the trade-off regarding the speed of these different algorithms, including the situation where you add minimization to the deep learning methods?
So I did not benchmark the speed of the individual methods. The energy minimization is not saving you, however, because it is quite slow. So energy minimization, if that was sort of like, if you had all the time to do energy minimization, you might have done molecular dynamics with like a, you could try a very simple approach, just plugging the ligand sort of in like an open space in the protein, in the approximate binding site and minimize the energy. Maybe that will work. The drawback there is, of course, you don't have the time if you were doing many, many complexes.
But I'm wondering, versus your classical benchmark.
I didn't measure it, but I know that Gold and Vina were quicker based on running them. That's all I can say without having, run the numbers and tabulated them.
And in the current context, PoseBuster seems to be mostly threshold based. Could you imagine taking those rules and turning them in something that could be minimized quicker than the usual force field minimization method?
So it's kept simple on purpose. We don't want to reinvent the wheel because that's kind of what a force field does. It implements sort of the physical understanding of what these things should look like, and then you can minimize. Maybe there's an intermediary. I thought it'd be interesting actually. One could do this empirical based. So there is a lot of crystal information, proteins with ligands and just molecules alone. And one could compare against, how often do you see a certain molecular conformation in that database? That's another way you could use to verify this. And I'm sure, and there's programs from the CCDC, like ISOStar and Superstar, which already do this, which is, I guess, another way to look at this. But we are not gonna, or I wouldn't change PoseBusters from the current simple approach, or that's at least not planned.
Okay, cool. Thanks. Great talk.
Daniel?
Yeah, I was just curious if you have any intuition as to like what we need in deep learning models to start to match the performance of the classical docking methods. Like, do we need a new type of inductive bias or something else?
That's a really good question. So I guess the first thing would be methods which don't fail the tests as they are defined. The different methods fail in different ways. Some of them, they fail with bond lengths. So maybe the method can be constrained to be, predicting bond lengths within certain distances. Maybe there's an inductive bias, as you say, that you could put in. I guess overall, people are thinking of combining physics with deep learning. Deep learning being like a general description, which is if you use a full force field, slow to compute. Deep learning potentially much faster. So, maybe there's a way to combine the two to make virtual screening sort of feasible. What exactly it is, I don't know, but I'm definitely going to try out some ideas.
Awesome. Thanks for the talk. It was really good.
One question by Jakub in the chat. So the overestimated performance of the deep learning based method is simply an effect of the bad split and information leakage. Is that correct?
I want to say yes, and the but is going to be the use case that you look at, because there might be use cases in which you actually are trying to do drug discovery on a protein that you actually have a lot of crystal structures for. So, and then on the other hand, you can imagine another scenario in which you're trying to predict molecule poses for a protein for which you haven't observed crystal structure. Those are very different scenarios in which you might apply docking methods. So what I'm saying is that you want to measure performance of those methods for different use cases, and then report exactly the performance on the use case that is, closest to the use case that you're going to be interested in. There isn't like a one. Yeah, you can't just do one sort of benchmark and say my docking method is the best, because there might be a scenario which is different from the one you've tested. So what I'm saying is we want to have different types of comparisons for docking methods, different types of data splits, and different levels of information leakage, because by itself, that's not a bad thing if your method is able to learn from what is known for a problem that is sort of related.
Okay, perfect. A question from Maria. Why did you decide to use such a huge binding box definition for gold and a smaller but still huge for Vina? Did you account for adjusting the default setting with regard to the disk bus size?
So we made gold and Vina's search spaces bigger to be able to compare against the blind docking methods better. It's not perfect, of course, but we ran a test, and the figures are in the appendix, that if you make the gold search space smaller, it performs quite similar. So in a way, we've made it much harder for the classical methods to perform really well. So this is a bit of a make it really hard for the classical methods, keep the deep learning methods sort of the way they were designed, more or less, and then to compare the two, because we're always going to be comparing apples and pears, given that one is a constrained search space and one is a blind search space.
Thank you. I was actually quite surprised that they still perform that well with that big binding boxes. Thank you.
And I guess to your second question, I did not check the torsion angle distribution of all methods with respect to something like mobile. That might be quite interesting, actually.
Yeah, because for example, Vina, it doesn't have any good penalties for bad torsion angles. And I think gold might have them, but I'm not sure. So it could also produce some interesting distributions. And also there are always things like, I'm sorry if you hear my background, I'm like in a common room. Also, there are things like carbohydrates, right? And all the sugars, and they have particular torsion distributions, which are also interesting to compare.
Yeah, actually, I think that's a really cool idea. I don't think I
and
will
also
get around to do
peptides.
this. but that's a good point. You're saying that sugars, carbohydrates, and peptides, they have characteristic torsion angle distributions, which you would expect to meet